Hello everyone. Today we are going to talk about mixtures and spices. Let's first talk about mixtures. There are two kinds of mixtures, the discrete mixture and the continuous mixtures. Um, why do we need the discrete mixtures? For example, if we are modeling a homeowner insurance, claims of the homeowner insurance can be from different situations. For example, it can either be a fire, a burglary, or a liability accident. So we have to model these three kinds of situation, but it all pertains to the claims of the homeowner insurance company. So this will be a discrete mixtures. The definition of this discrete mixture is that a random variable y is a discrete mixture or finite mixture of random variable x1, x2 till xm if its probability function can be expressed as a weighted average of the probability function of these n random variables. So y is also called n-point mixture. So here is the formula where w is the weight of random variable xi, then weights should have the following properties. The sum of the weights should be equal 1, and each weight should be less than 1 but greater than less than or equal to 1 but greater than or equal to 0. The following is a simple question. Let x be a mixture of exponential distribution with mean theta1 and weight w1 and exponential distribution with mean theta2 and weight w2. Then fx is what? So yeah, before we answer these questions, I also want to mention that for PDF you have this quality. Then similarly for FY, which is CDF, for PDF you have this quality, and for CDF you will have the same quality. And similarly for survival function or expected value, they all have the same kind of property. Okay, now we can answer these questions. So it's fx is equal to w1 times 1 minus e negative x over theta 1 plus, so similar w2 times 1 minus e negative theta 2. Then if we consolidate these two, w1 and plus w2 will become 1 because here there are only two weights, w1, w2, so it add together to be 1, so it will be 1 minus e x theta 1 minus e x theta 2. That's the answer for this. Okay, this slide is about the moments for a mixture distribution. You can see it follows the same formula as PDF or CDF. The mean of this EX is the weighted sum of each EXI. Similarly for second moment or nth moment. And for variance, we know the variance formula, then we will be able to calculate that for a mixture distribution too. Okay, let's look at some examples. Example A, if x be a mixture of an exponential distribution with mean 100 and weight 60%, and an exponential distribution with mean 200 and weight 40%, calculate the probability of x less than or equal to 100. If we recall from previous slides that if we want to calculate the probability for this mixture distribution, first we want to calculate the probability for each xi's probability. Then we use the weighted sum to calculate the probability for x. So first we will do p x1 less than 100, which this is an exponential distribution, so we know it's 1e negative 100 over theta 1, which is 100. So here we can get 0.6321, and similarly we know we need to get the x2, which is, except here you have a theta 2, which is 200, so you get 0.3935 here. Then eventually you will get x, which is just weighted sum. So weight by first one is weight by 60%, plus second one is weight by 40%. Then you will get the final result to be 67. Okay, so this is a very simple example just to demonstrate the formula. Now let's look at example B. Losses on a auto liability coverage follow a distribution that is a mixture of two Paretos. Each distribution in the mixture has equal weight, which means the weight is 50%. One distribution has parameters alpha equals 3 and theta equal 1000, and the other has parameters alpha equals 3 and theta equal 10,000. Find the PDF for loss. So we know the PDF of this loss, which is a mixture distribution, should be the weighted average of each PDF. So first we want to write it out as this. First we want to review the Pareto distributions PDF. We know the PDF for Pareto distribution, I believe, is alpha theta alpha x plus theta alpha plus 1. So once we know this, it will be easier to write it out. So weight, we know the weight, equal weight means the weight is 50% for each. So the fx can be write as first one 0.5, then alpha is 3, theta is 1000, divided by x plus 1000 to the fourth power plus 0.5. Here alpha is 3, but here is 10,000, so it's 12 times x plus 10,000. So this is the PDF of the loss. The second question for this example B, find the CDF of a loss and determine probability x greater than 1000. First, we still need to review the fx for the Pareto distribution. Fx for Pareto distribution is 1 minus theta plus x raised to the power of alpha. So with that, then we should be able to calculate this CDF or fx. Fx will be equal 0.5, 1 minus 1000 x plus theta raised to the alpha 3 power plus, okay, this plus 0.5, 1 minus 10,000 divided by x plus 10,000 alpha here. Okay, now we can further consolidate it to be 1 minus this and list item. I'm not going to write it again. And after that, after that we will put the x greater than 1000, calculate this will be 1000. So we put 1000 in the x in the place of x, then you will calculate the result. Plus 10,000, 11,000, and finally we can get a result to be 4382. The third question of this example B, calculate mean and variance of a loss. First, we want to reveal the expected value for a Pareto distribution, which is Ex is equal theta alpha minus 1, and here alpha is greater than 1. And we also want to know the since it is asking for variance, then we need to know the second moment. Ex squared, which is 2 theta squared times alpha minus 1, alpha minus 2. So once we get this, we should be able to calculate the expected value for each of these Pareto distribution. Okay, so Ex1 is theta is 1000, alpha is 3, so 3 minus 1, so it's 500. Ex2 is 10,000, 3 minus 1 is 5,000. Therefore, Ex is the weighted average of these two with 0.5, 500 plus 5,000, which is equal to 2750. Now let's calculate Ex squared. Ex squared based on this is 2 times 1000 squared times 3 minus 1, 3 minus 2, basically is 10. This 2 here is cancel out, and this is 1, so basically it's 6 power. This is x1. Ex2 will be, based on this, it's easy to determine is 10 to the 8th power, because the only difference is here. Now we can get the Ex squared will be the weighted of these two, so it's 0.5 plus 50500000. Then variance, we can use this formula, Ex squared. This is a formula that we will use a lot too, and we need to remember. Then we can put the numbers in. Eventually you will get this. Now let's look at example C. On auto collision coverage, there are two classes of policyholders, A and B. 70% of drivers in Class A and 30% in Class B. The means and the variance of losses for the drivers are as follows. A claim is submitted by a randomly selected driver. Calculate the variance of the size of the claim. Again, we know the formula for the variance. VARX is equal Ex squared minus Ex whole thing square. So we need to find out this ex square and ex, then we will be able to find out the varx. From what is given, we will first, based on this, actually we can calculate the ex square. So ex square is varx plus ex, the whole thing square. So here ex square we can calculate. First one is varx 30,000 plus 300 square, which is 120k. And the second one similarly 50k plus 800 square, 64690k. So once we have that, the second step we can calculate ex equal 300 plus weight. For the second one is so this is 210 to 450, and ex squared similarly can be calculated as 120k plus 0.3 times 690k, so it will be 291k. Now with this we can calculate varx is equal ex squared, which is 291k minus 450 square, which is 88500. So what we need to know here is just that to calculate variance, we do not use the weighted average of variance. Rather, we use this formula because weighted variance of the mixture distribution is not doesn't have the property of weighted average of each variance. So rather we should use this formula to calculate the variance for the mixture distribution. So previously we talked about discrete mixtures. Now we are going to talk about continuous mixtures. So conceptually, in continuous version of mixing, where the discrete probability are replaced by the PDF of a continuous random variable. So in actual terms, continuous mixtures arise when a risk parameter from the loss distribution is uncertain and the uncertain parameter is continuous. Let's look at this example. Maybe it's a little more clear than the words. Suppose that the uncertain parameter x lambda is a continuous random variable with PDF f lambda. Let x be a random variable that depends on a parameter lambda. We say that x is a mixture of a distribution if its PDF is fx equal integral from negative to positive of fx depending on lambda and times f lambda d lambda. Now let's look at a more concrete example. The number of losses on a homeowner policy is binomially distributed with parameter m equal 5 and q. The parameter q varies by policyholder uniformly between 0 and 0.4. Calculate the probability of 2 or more losses for a policyholder. Okay. So from this, first we look at the Q vary by policyholder uniformly. So it tells us it is a uniform distribution where you have the PDF is equal 1 over B minus A, and this is 1 over 0.4. Then second, we are looking at the probability of 2 or more losses for a policyholder. To calculate the probability of 2 or more, the easiest way is we use probability of 1, 0 and 1. We calculate this first, then we use 1 minus all these 2 to get the probability of P equal to 2. Now, when probability n equals 0 and probability n equals 1, which are the binomial distribution. So then from the table of exam table, we know the binomial distribution. So P0 is equal this, P1 is equal this. With this in mind, then we can integral this over the distribution of Q, which is uniform distribution. So when P equals 0, we integral between 0 to 0.4. We apply this into the probability, and this is the result. Previously, we calculate P n equals 0, probability n equals 0. Now we are calculating probability n equals 1. Similarly, n equals 1, depending on Q, will be this. This is already derived in previous slides. It's just applying the formula of a binomial distribution. And we want to integrate this over Q, which is a uniform distribution with the fx is this. So this is the result. Then finally, we can calculate the Pn equal P probability of n is greater than or equal to 2 is 1 minus these two together, and we got this. And there's a little trick in doing the integral of this. The easiest way to do it, you substitute 1 minus q by u, and because this du is equal negative dq, you can do it. The integral will become from here to will become here. Then eventually it's easier to consolidate, and you will get here. This is where you can calculate the integral. Then you can substitute with the actual values in to get the final result. But this part is really just integral. It's not the knowledge of this course. Earlier we talked about mixtures, but really we need to talk about conditional mean and variance, because this is the foundation to calculate the mean and variance for mixture. So first thing we want to talk about is the law of total probability. If you are not familiar with this, the law of total probability states that if events A1, A2 until Am are mutually exclusive and form a partition of a sample space, then probability of B is equal to the sum of probability B intersect with each of AI event. So I is from 1 to m. This can be further converted to probability of B given event AI happened times probability of AI, and you sum them up for I from 1 to m. If we apply this concept to continuous mixture, meaning if event A is a continuous event, then there is no PMF, there is a just a PDF, then we have to use integral to calculate the probability of x. So similarly, uh, this represents probability when x equal small x will be the probability of x equals small x given y, but use the weighted average or integral to do it. So loosely speaking, the random variable y takes place of ai in this formula. The subscript y indicates that y is the random variable for the averaging. In other words, if y is discrete, then probability of x equal small x is the sum of probability of x equal x small x given y equals small y times the probability of y equals small y, and you sum them up for all y. But if y is continuous, then probability of x equal small x will be the integral of probability of x equals small x given y equals small y times the PDF of y, and you integrate it from negative infinity to positive infinity. Now we can look at the law of total expectation, which says the expected value of x is the expected value of the expected value of x given each y. So since there are two cases, discrete or continuous, the proof can be for both are listed here. If we look at the left side, that's the continuous case. Right side is a discrete case. This will not be tested in the exam, but I think you guys need to understand this because this is fundamental for some of the calculation. I'm not going to further talk about this. You guys can read it, and if you are not, you don't understand, feel free to contact me regarding this part. We talk about the law of total probability and law of expectation. Now we talk about law of total variance. The law of total variance states that a variable of x will be the expected value of a variable x on x condition on y plus variable of variance of y on ex expectation of x condition on y. So the right side is the proof of this concept or this law. Again, I will leave this for you guys to read. Now let's look at this example. The number of losses on a homeowner's policy is binomially distributed with parameter m equal 5 and q. The parameter q vary by policyholder uniformly between 0 and 0.4. Calculate the variance of the number of losses for a non-randomly selected policyholder. From this, first we can tell that the loss, if we note it as m, would follow the binomial distribution with parameter 5 and q. So n is depending on q, and q follows uniform distribution from 0 to 0.4. With this, first we can calculate the EQ for, because this is the easier part. Then we apply this variance for the formula for this mixture. Then first we need to calculate the VA. We know the VAR variance of m given q is 5q times 1 minus q, and expected value is this can be found on the binomial distributions expected value and the variance. Then further, you can just utilize the formula to calculate the result. Final result will be here. Example B. Claim size ranged between 0 and 1500. The probability that the claim is no greater than 500 is 0.8. Claim size a uniform distribution distributed on 0 to 500 and on 500 to 1500. Calculate the coefficient of variance of claim size. So first, if x1 is between 0 and 500, the expected value is 250. Second moment, or the expected value of x squared would be this much. This can be carried. This is just the uniform distribution. Then, similarly, if x2 is greater than 500 or 1500, you can calculate the ex2 and the ex2 square. Still, these are the uniform distribution. Now, the mixture is the mix of these two distributions. So, ex is the weighted average of these two, which get to 400. Ex squared can similarly be calculated here. Then the variance can be calculated here. With the variance calculated, then you can have the coefficient of variance, which is omega over mu. The next concept we are going to talk about is splice. The idea of splicing is to combine different probability distribution over different intervals to produce a new distribution. Splice is different from mixture in that splice you have two probability distribution, but each applying to certain interval. They are not overlap. While the mixture, your two distributions are both applied to the whole interval, and you are just taking the weighted average of the two. So those are the differences. And the reason to have a surprise is because sometimes actually feels like the random variable cannot be expressed as one single distribution. Maybe they feel, for in this example, they feel when the revenue is small, it follows exponential distribution. But when the revenue is higher, they follow the Pareto distribution. That's why they just use part of exponential and part of Pareto to represent this new random event or this new random variable revenue. That's what we are talking about. So in general, a random variable y has a splice distribution if it has the probability function that can be expressed as follows. The things that we need to know is that the Ci here is not a weight. It's not a weight, so it doesn't have to sum to 1. However, the coefficient are non-negative because a valid PDF cannot be negative. The CIs are chosen such that the probability function of y integral or sum to 1. Let's look at this example. Loss sizes follow a splice distribution. The probability density function of this distribution below 200 is a multiple C of the probability density function of an exponential distribution with theta equal 300. The probability density function above 200 is the same as an exponential distribution with theta equal 400. Calculate the probability that a loss is less than 100. So what they're asking is about probability of p less than 100, which is based on first one is below 200, then it's a multiple of c, and this part is just the formula of exponential. Now the question here is, we don't know C, because how do we get C? That's where we utilize what we talked about earlier. The probability total of probability should sum up to 1, which means P x less than 200 plus P x greater than 200 together should be 1. And when x is greater than 200, we know it follows this. Theta is 400. So this part we already know. This part is C 1 minus E 200 over 300. Theta is 3 here. So we add these two together should equal 1. From here, we can get C is equal 0.0807. Then with this C, we can calculate this. So this will be 0.0807 times 1, and you can get this 0.229. So here we just utilize the property that the total probability should be equal 1 to derive C. With that, then we should be able to calculate probability.